Okay, currently I'm back, Professor Bill Mwanza, to continue on Hooke's law, and that is the factors affecting the spring constant, or let me say, these are the factors affecting spring constant, or someone may say factors affecting the stiffness of the material, spring constant of the material, or someone might say factors affecting the stiffness of the material. Okay, factor number one, as you know, factor number one is the nature of the material. Now, the nature of the material, how can we explain this? The nature of the material. If someone asks you to explain factors affecting the spring constant, and you just know that the nature of the material is one of the factors, how can you explain this? Okay, this is how you go. A material with an ability to stretches to a longer distance compared to that does not stretch. Or I can write a material that have an ability to stretches to a longer distance compared to that one that does not have ability, or that one that does not stretch. For an example, if I give you a piece of wood and a thread, and not a thread, and a spiral spring. A spiral spring is such a material that have an ability to stretch. Now that one will stretch to a longer distance. Not even to a longer, it will stretch. That is possible. But the possibility there is just it will stretch. As compared to a material that does not stretch, for example, a piece of wood or this pen. If I take this pen, it doesn't have an ability to stretch because it is not an elastic material. Now, even if I do like this, even if I apply force, opposite forces, it will not stretch because this one doesn't have an ability to stretch. Now, factor number two. I wanted to begin on factor number 2 and number 3 because they coincide. Factor number 2, it is the thickness of the material. Thickness of the material. Okay, how does this affect the material? Okay, or what is the thickness of the material? The material that used to make the spring or the spiral spring. This is how you explain this. A material with a thicker cross-sectional area, with a thin cross-sectional area, stretches to a longer distance. A material with thin cross-sectional area stretches to a longer distance compared to that with thick cross-section, to compare that with thick cross-sectional area. I can demonstrate. For instance, if I give you a spiral spring like this one, if you compare this spiral spring with this one, Okay, the thickness that I'm talking about, it is this one. Look at the thickness of this wire at this point and the thickness of this wire at this point. Now this wire has a very, it is thicker as compared to this wire at this point, or this spring. This one is thin as compared to this one. Now this one will stretch, has a very high ability to stretch as compared to this one, because the thickness of the cross-sectional area of the wire, it is smaller as compared to the thickness of the cross-sectional area of this second wire. This scenario 1, this scenario 2, and this scenario 1. Or if someone doesn't want to talk about the thickness, he or she can talk about the cross-sectional area. Now this is the cross-sectional, the wire is this one. Now the wire, the cross-sectional area of this wire, it is the thickness of this wire at this point. And the cross-sectional area of this wire, it is the thickness of this wire at this point. Now this one, the cross-sectional area of this one, it is bigger or it's larger as compared to the cross-sectional area of this wire at this point. Now this wire will stretch to a longer distance compared to the other, because the cross-sectional area of the wire is smaller than the cross-sectional area of the wire 2. Now this one will stretch to a longer distance. But the best way to use it, if you use the cross-sectional area, it will challenge you. Maybe with the third point that I want to give you, you rather use the thickness of the material, because if you say the thickness of the material, a material with thin, this one is thin, cross-sectional area stretches to a longer distance as compared to a material with the thick cross-sectional area. Now let's look at the third factor. Third factor, what can we say? Third factor, we look at the diameter of the coil used to make the spring. This is the diameter of the coil used to make the spring. Okay, how? Let me explain it further, then I can give you a demonstration. Now, this is what we say. A wire or the spring with a larger diameter of the coil, a material with larger diameter of the coil stretches a longer distance as compared to that with the shorter diameter. A material with larger diameter of the coil, most probably we're looking at this coil, the diameter of the coil stretches to a longer distance as compared to that with a shorter diameter of the coil. Now what are we looking at? Now the scenario is this one. If I draw the first coil, this is the first coil. And the second coil is this one. Now if you look at these two wires, as you consider the second factor, which is the thickness of the material, the thickness is equal. Now let's look at the diameter. The diameter of the coil. We are emphasizing on this diameter of the coil, nothing else. If you just say diameter, someone might think that we are talking about the diameter of the wire, but you're talking about the diameter of the coil. And the coil, it is the distance from here up to here. Now the diameter of the coil is from this one up to this one, and the diameter of this other coil is from this point up to this point. Now this one is like 2 centimeters and this one is like 4 centimeters. It means the one with the larger diameter of the coil will stretch to a longer distance as compared to this one. Those are the three factors affecting the stiffness of the material, and I told you the stiffness means the spring constant. Okay, from there let's look at another subtopic, which is work done to stretch a spiral or a spring or a material. Work done to stretch. Work done to stretch a spring. Okay, for your information, you know that work done, there must be force applied and the distance covered, or the force applied on a material through a distance, that one will find work. If I apply a force on this spring and allow this, and the force I apply on this spring make this spring to stretch through a distance, now that means there is work done. And if you want to know the work done, let's look at the scenario whereby we have a curve, a graph of this y-axis, this x-axis, and on y-axis we have force. On x-axis we have the extension. On x-axis the extension is at this point. On y-axis the force is at this point, and everything starts from 0. It means the graph drawn will be this will be the example of the graph which will appear, and the graph is a straight line through the origin, the center. I can complete it like this to form such a triangle. And you know very well that from the formula, force is equals to KE. From the previous lesson, we said that force is equals to KE. Now I can say this is a straight line, and a straight line can give us an equation of a line. An equation of a straight line, it is y is equals to mx plus c. And the factor that is on y-axis, it is this force. Now I can place here force is equals to the one on the x-axis. On the x-axis, it is this extension. Now I'll have here an extension. The one the value the coefficient of this x, it is the gradient. Now the gradient, it is the constant. Now here is where we have the constant. Now the plus c, this c here, the c we have, it is 0, because the c is the value where the y-intercept, where the c is the value of y-intercept, where the curve or the graph cuts the y-intercept, and as you can see, it cuts the y-axis at 0. Okay, that means if you want to find the equation of this line, you will find the area under this graph, and the area under this graph will give us the work done. The area under this graph will give us the work done. Or let me say the area under this graph, it is a half base times height from the basic formula of mathematics. And it is a half, our base, it is extension. From here up to here we have extension. Now a half times extension times height. Our height from this point up to this point coincides with the force. Now our height is the force. Now the area under the graph, I've given you that the area under the graph gives us work. Now our work will be half force times extension. That is work done. That is the formula for work done. For example, you can be given a question. This is the formula. Force times extension, or extension times force multiplied by half. For example, determine the work done in stretching a spring if the force of 0.2 newtons produces an extension of 0.0003 meters. Now we have been told, find the work done. Determine the work done if the force applied was 0.2 and causes an extension of this one. And I've said work is equals to half times force times extension. This will be a half times our force is 0.2 times extension is 0.0003. Our answer will be 0. This 2 will go into 0.2, 0.1. Now we'll have 0.00003. That is the value will be force is in newtons times extension is in meters. Now we have Newton meter because we have multiplied. Now our answer will be Newton meter. Or someone else can write 3.0 times 10 raised to power 5. Then this will be Newton meter. Now that is work done. You can be given so many other questions where you can search from the past papers as long as you use this basic knowledge from here. Now, let's finalize on one thing. That is the combination of the springs. As you know, springs can be combined. We have been using one spring, one spring, one spring, one spring. Now, in any occasion that you have been given the 2 or 3 springs, maybe arranged in different combination, how can you get the spring constant? How can you get the extension of the total system? Now, when the springs are used more than one, it's called a system of springs. Now, for instance, you have a spring, the first spring, that one. This spring has been attached to another spring. Then there is a load down here. Now this arrangement is called series arrangement. It's called series arrangement. Now, in fact, I've forgotten this combination of springs. Combination of springs. We are combining springs either in different types of arrangement, and we only have 2 arrangements. That is the series arrangement and the parallel arrangement. The parallel arrangement, this is the scenario. Now the series arrangement, the springs might be even 7, but they have been arranged in this form. Then that is series arrangement. Now the second arrangement, it is this one. We have been given a spring like this one, another spring, this spring too. Now this arrangement of the arrangement of the spring below, it is known as parallel arrangement. Parallel arrangement. There is a situation where someone can mix the two, the series arrangement and the parallel arrangement. This is the scenario, and that is the third combination, whereby you have been given, for example,